Ever feel overwhelmed by complex chemistry, like wishing someone would just cut straight to the most important parts?
Yeah, absolutely.
Well, today we're doing exactly that. We're taking a deep dive into a really foundational concept, acid-base reactions in organic chemistry.
Hmm.
And this isn't just, basic stuff. It's kind of the bedrock for everything else that comes after.
It truly is. And
Yeah.
for this deep dive, our main source is Organic Chemistry as a Second Language, first semester topics, the 4th edition, specifically Chapter 3.
Okay.
Our mission, really, is to demystify why acid-base chemistry is introduced so early on,
Right.
and also uncover the critical factors that actually determine acidity and, well, arm you with practical problem-solving strategies,
Yeah.
stuff that will serve you throughout organic chem.
Yeah, and at its heart, it all boils down to one, maybe surprisingly simple concept, charge stability.
That's the one.
If you can truly master that, organic chemistry suddenly starts speaking a much clearer language, doesn't it?
It really does.
Okay, let's unpack this.
So what is an acid-base reaction in this context? Fundamentally, it's just a proton transfer.
A proton moving around.
Exactly. Imagine a molecule, let's call it HA, acting as an acid. It donates a proton, H plus N.
Okay,
Then another molecule, B, acts as a base, accepting that proton.
right.
And what's left of the acid after it gives up its proton, that's AO. We call that its conjugate base. And now it's ready, potentially, to accept a proton back.
Okay, and this is where stability becomes like the ultimate driving force, isn't it?
Absolutely.
The core question is, how willing is that acid, HA, to actually give up its proton?
Mm-hmm.
And that willingness depends entirely on how stable the resulting conjugate base A is once it's carrying that negative charge.
Exactly. So if the conjugate base is very comfortable, you could say, with its negative charge,
Okay.
meaning it's highly stable,
Mm-hmm.
then the acid will be pretty eager to donate its proton. That makes it a strong acid.
Right. Strong acid, stable conjugate base.
But if that negative charge makes the conjugate base really unstable, maybe unhappy,
Unhappy base.
yeah, then the acid will cling tightly to its proton. It won't want to let go. And that makes it a weak acid.
Weak acid, unstable conjugate base. It's an inverse relationship.
Precisely. And this ability to just instinctively look at a negative charge and assess its stability, it's not just a skill, it's kind of your organic chemistry superpower.
I like that superpower.
Because reactions fundamentally are just a dance of charges. And if you don't grasp what makes a charge stable or unstable, you'll struggle to understand the choreography, the whole dance.
Yeah, you won't know the steps.
Right. That's why this concept is introduced so early. It's foundational. It unlocks the logic behind almost every single reaction you'll encounter later on.
So if charge stability is our guiding principle, our North Star, what's our toolkit? How do we actually predict it in a molecule?
Good question. The source highlights 4 crucial factors for stabilizing a negative charge. It gives us a clear roadmap.
A roadmap.
We'll go through them one by one. Think of it like a checklist or an easy-to-remember acronym, ARIO.
ARIO. ARIO. Got it. Not a cookie, but important.
Exactly. So let's dive into factor 1. What atom is the charge on? This is often the most important factor to consider first.
The atom itself matters most.
Often, yes. When you're comparing 2 negative charges, your very first step is always to look at the atom holding that charge on the periodic table. There are 2 main scenarios here.
Okay, scenario 1.
First, if you're comparing atoms in the same row of the periodic table, say carbon versus oxygen.
Like going across.
Yeah, going across. The trend is electronegativity. As you move right across the table, electronegativity increases.
Meaning they pull electrons harder.
Exactly. Think of it as an atom's magnetism or greediness for electrons. Oxygen is more electronegative than carbon. It has a stronger pull.
Right.
Therefore, a negative charge sitting on a more electronegative atom like oxygen is significantly more stable than the same charge on a less electronegative atom like carbon. Oxygen is just, well, better equipped to handle those extra electrons.
Okay, so across a row, electronegativity wins. What about moving down a column? Like fluorine versus iodine. My gut says fluorine wins. It's super electronegative.
That's a great question, and it's where the second scenario and often the confusion comes in.
Ah.
For atoms in the same column, the trend is actually size.
Size, not electronegativity.
Size dominates here, and yes, it often feels counterintuitive. While fluorine is indeed way more electronegative than iodine,
Right.
the sheer size difference is what determines the stability. Larger atoms can spread that negative charge over a much larger volume, a larger space.
Oh, okay.
This dispersion, it dilutes the charge density, making it inherently more stable.
Hmm.
So an iodide ion, IO, is actually much more stable than a fluoride ion, IO, precisely because iodine is so much larger, even though it's less electronegative.
Okay, that makes sense. It's like spreading peanut butter thinly over a huge piece of toast versus a big blob on a tiny cracker.
That's a perfect analogy. The mansion versus the small house party works too. The mansion spreads everyone out.
All right, so for atom, electronegativity rules across a row, size rules down a column.
Got it. And how do these two effects compare? Like, which one usually has a bigger impact?
Good point. Generally, the electronegativity effect, when comparing atoms in the same row, is a much stronger, more dominant effect than the size effect when comparing atoms down a column.
So check the row first, usually.
Pretty much. It's almost always the first thing you check. And as a practical problem-solving strategy, when comparing acidity, always remove the proton question.
Okay.
Draw the resulting conjugate base with its negative charge.
Visualize it.
Yes. Then compare the stability of those negative charges using these trends. For example, comparing a proton on oxygen versus one on nitrogen. Remove H plus A, you get O versus N. Oxygen is more electronegative.
So O is more stable.
Right, which means the proton on the oxygen was more acidic to begin with.
Okay. ARIO, A is atom, done.
What's R?
R is resonance. We've touched on resonance before, and it's absolutely everywhere in organic chemistry. Plays a massive role in acid-base behavior.
Right, the shifting double bonds and stuff.
Sort of. But remember, resonance doesn't mean structures rapidly flipping back and forth.
Oh, right, it's not an equilibrium.
Exactly. It means there's only one true chemical entity, one structure, where the charge is actually delocalized, spread out over multiple atoms, rather than being stuck or localized on just one.
Okay, delocalized, spread out, like that hot potato analogy.
A hot potato analogy is perfect. If you're holding one really hot potato, it's uncomfortable, unstable.
Yeah.
But if you could magically split that heat and spread it over two potatoes, suddenly each one is much cooler, much easier to hold, more stable.
So spreading the charge makes it more stable.
Always. It's the same concept with a negative charge. Spreading that heat, that negative charge over multiple atoms makes it significantly more stable. A delocalized negative charge is always more stable than a localized one stuck on a single atom.
And that explains certain acids.
Absolutely. This delocalization is precisely why carboxylic acids are, well, acidic. When a carboxylic acid loses its proton, the conjugate base it forms.
The carboxylate ion.
Yes, the carboxylate ion. It has its negative charge beautifully spread across two oxygen atoms via resonance.
Ah, across both oxygen.
Yep, this delocalization makes that conjugate base incredibly stable, which, going back, makes the original acid quite willing to give up its proton, makes it quite acidic.
Okay, so resonance is a big stability booster. What if you're comparing two different bases and they both have resonance? How do you decide which is more stable?
Good question. There are a couple of sub-rules there. First, generally, the more atoms the charge is delocalized over, the better. Spreading over 4 atoms is usually more stable than spreading over just 2.
More spreading is better? Makes sense.
But there's a critical nuance. The type of atom matters too. Spreading a charge over electronegative atoms, like oxygen, is generally much better, much more stabilizing than spreading it over carbon atoms.
Even if there are more carbon atoms involved.
Yes. So a negative charge spread over 2 oxygens is generally more stabilizing than spreading it over, say, 1 oxygen and 3 carbons, even though the latter involves more atoms overall. Oxygen handles negative charge better.
Okay, quality over quantity sometimes. So comparing, say, a localized negative charge just sitting on a nitrogen versus one that's delocalized over both a nitrogen and an oxygen through resonance.
The delocalized one wins, hands down.
Because resonance is spreading it out and onto an oxygen which likes negative charge.
Exactly. The delocalized one is way more stable, meaning the proton that leads to it is more acidic. Resonance is a truly powerful stabilizing force.
Okay, A is atom, R is resonance. What's I in ARIO?
I is induction. This is a bit subtler maybe than resonance, but still a powerful force.
Induction. That sounds familiar. Has to do with electronegativity again and bonds, like oxygen pulling electrons in a CO bond.
You're absolutely on the right track. Induction is all about that pulling of electron density, but specifically through sigma bonds, those single bonds forming the molecules of backbone.
Okay, through the single bond.
Yes. And it's driven by differences in electronegativity. Like you said, in a CO bond, oxygen pulls the shared electrons closer, making oxygen partially negative and the carbon partially positive. GREL plus AC.
Okay, So how does that stabilize a full negative charge somewhere else in the molecule?
Well, imagine you have highly electronegative atoms, like, say, chlorines or fluorines, attached near a negatively charged region in a molecule.
Okay, nearby electronegative atoms.
These electron withdrawing groups can pull electron density away from that concentrated negative charge through the sigma bonds. It's like they act as tiny vacuum cleaners.
Sucking the negativity away, metaphorically speaking.
Metaphorically, yes.
Yeah.
They subtly disperse the negative charge, pulling some of that electron density towards themselves, which stabilizes the overall species. It reduces the concentration of charge.
Interesting. Does it matter how close these vacuum cleaners are?
Oh, absolutely crucial detail. Inductive effects fall off rapidly with distance.
Yeah.
The closer the electron withdrawing group is to the negative charge, the stronger that stabilizing pull will be. 1 carbon away is strong, 2 carbons away is much weaker, 3 is almost negligible.
So proximity is key for induction.
Definitely. So if you're comparing 2 conjugate bases, and one has electron withdrawing groups like 3 chlorines right next door to the negative charge, and the other doesn't.
The one with the chlorines nearby will be more stable.
Exactly. And therefore, the corresponding acid will be stronger. For example, trichloroacetic acid is much stronger than acetic acid because those 3 chlorines inductively stabilize the negative charge on the carboxylate.
Okay, atom, resonance, induction. That leaves O. What's O?
O is orbitals. This one gets a little bit into molecular geometry, the shapes of molecules, but don't worry, it's actually pretty straightforward once you see the pattern.
Orbitals, like SPDF, or the hybrid ones.
The hybrid ones, we're talking about hybridized orbitals,
Hmm.
specifically ST3, SP2, and SEP.
Right, the ones related to single, double, and triple bonds.
Exactly. And what makes these different in terms of charge stability? Well, they vary significantly in their shape and how close they are to the nucleus.
Okay.
The k orbitals, the ones associated with triple bonds, are the smallest and tightest of the 3. They have more Cs character, which means they hold the electrons closer to the positively charged nucleuses of the atom.
Closer to the positive nucleus.
Yes. And being closer to that attractive positive charge means a lone pair of electrons, and thus a negative charge residing in an sp orbital will be more strongly stabilized than if it were in a larger, further out sp2 or sp3 orbital.
So closer is more stable because of the attraction to the nucleus.
Precisely. It's like a closer, stronger gravitational pull holding onto those electrons.
Okay, so how do we quickly figure out if we're dealing with SPs, sp2, or sp3 just by looking at a structure?
There's a simple rule of thumb, especially for carbon. A carbon atom involved in a triple bond is sp hybridized.
Triple bond sp2.
A carbon atom involved in a double bond is sp2 hybridized.
Double bond sp2.
And a carbon atom with only single bonds is sp2 hybridized.
All single bonds equal sp3. Got it.
So the result is a negative charge sitting on a sp hybridized carbon is significantly more stable than the same charge on an sp2 or sp3 carbon.
Because that sp orbital holds it closer to the nucleus.
Exactly. Therefore, a proton attached to an sp hybridized carbon will be surprisingly acidic, more acidic than protons on sp2 or sp3 carbons.
So to apply this, you'd look for protons on carbons with triple bonds, basically.
That's the main place you see it. You'd identify the most acidic proton in a compound, perhaps, by checking which one, if removed, would leave behind a negative charge in an sp orbital.
Okay, that covers A, R, I, and O, the 4 factors.
Right. Now, we've gone through them individually, but it's absolutely crucial to understand their relative importance. When you're trying to compare 2 different protons, you don't just pick a factor randomly.
There's an order to it.
There's a hierarchy. In general, you apply these factors in a specific ranked order. First, and usually most important, atom. What atom is the charge on? Electronegativity versus size.
Check the atom first.
Then, second, check for resonance. Is the charge delocalized? Resonance is a powerful stabilizer.
Okay, atom, then resonance.
Third, look for induction. Are there any nearby electron withdrawing groups pulling density away?
Induction is third.
And finally, fourth, consider the orbital. What type of hybridized orbital is the charge actually sitting in? sp, sp2, or sp3?
Atom, resonance, induction, orbital, ARIO. That's the priority list.
That's your standard roadmap, ARIO.
But you said standard implies there's something non-standard. Here's where it gets really interesting. You mentioned a curveball earlier.
Yes, the curveball.
Mm-hmm.
You need to pay close attention here because there's a critical exception to this ARIO ranking. It's famous, or maybe infamous.
Okay, I'm listening. What's the exception?
The key exception comes up when you're comparing an sp hybridized carbon with an sp3 hybridized nitrogen.
Okay, sp carbon versus sp3 nitrogen.
Normally based purely on factor 1, the atom factor, you'd expect the negative charge on nitrogen to be more stable, right? Nitrogen is more electronegative than carbon.
Right, Adam says nitrogen wins.
But this is one of those rare specific cases where factor 4, the orbital factor, can actually win out over factor 1, the atom factor.
Whoa, orbital beats atom. How?
Because that negative charge on the hybridized carbon is held so incredibly close to the nucleus in that very tight, very stable orbital,
Right, the closeness effect.
that it actually becomes more stable overall than a negative charge on an sp3 hybridized nitrogen, even though nitrogen is more electronegative. The orbital effect is just that strong in this specific comparison.
So let me get this straight. A negative charge on an sp3 carbon is more stable than on an sp3 nitrogen.
Correct, which means flipping it around, a proton on an sp hybridized carbon, like in a terminal alkyne, is actually more acidic than a proton on an sp3 hybridized nitrogen, like in ammonia or an amine.
Wow. Okay. And that explains certain reactions then.
It does. This is precisely why you can use a strong base like the imide ion, NH2O, where the charge is on nitrogen, to deprotonate a terminal alkane, pulling off the proton from the sp hybridized carbon. Normally N beats C, but here the sp orbital on C makes that proton acidic enough for the nitrogen base to grab it.
That's a really important exception to remember. SpCH is more acidic than sp3NH.
It is. It's a specific but crucial scenario. But remember, while this exception is vital for cases like that, for most of the qualitative comparisons you'll make, the standard ARIO ranking is your reliable guide.
Okay, stick to ARIO unless it's specifically sp carbon versus sp3 nitrogen. Got it. Now, everything we've discussed so far helps us compare relative acidity, which proton is more acidic.
Right, qualitative comparisons.
But what if we want to put a number on it to know how much more acidic something is? That's where pKa values come in, right?
That's exactly right. A pKa value gives us a quantitative measure. It's an empirically determined number, meaning it's found through actual experiments in the lab, not just predicted by looking at ARIO factors, although they correlate.
Okay, experimental numbers. And what's the rule for interpreting them?
It's simple but vital. The smaller the pKa value, the more acidic the proton.
Smaller pK equals stronger acid.
Yep. So a compound with a pK of, say, 4 is a much, much stronger acid than one with a pK of 7.
Okay. Do we need to memorize tables of these?
You don't necessarily have to memorize an entire pK chart, though knowing some key benchmarks is helpful.
Yeah.
But the crucial thing is understanding what the scale means.
Right. You said pK 4 is much stronger than 7. How much stronger? Is it like 3 units stronger?
No, not linear at all. And this is where it gets truly wild. The scale is logarithmic, like the pH scale.
Logarithmic, meaning powers of 10.
Exactly. A difference of just 1 pico unit means a 10-fold difference in acidity.
10 times.
Wow. So that jump from pK 7 down to pK 4 at 3 pK units. So that's 10 times 10 times 10.
1,000-fold difference in acidity.
1,000 times more acidic. And think about the difference between, say, a typical alcohol with a pK around 16 and an alkane with a pK around 50. The difference is enormous.
Mind-boggling scale. Okay, so pK gives us the quantitative picture.
It does. Very useful for precise comparisons.
So understanding these relative pKi values, or at least the underlying ARIO principles that lead to them, helps us in another key area, predicting the position of equilibrium in an acid-base reaction.
Absolutely. This is where it all comes together in a reaction context.
If you have two bases kind of fighting over a proton, how do you know which side the reaction prefers? Which side will have more stuff at equilibrium?
It all comes back, yet again, to stability, our core concept.
Stability rules all.
It really does. The equilibrium will always favor the side of the reaction that has the more stable negative charge. In other words, the side with the more stable conjugate base.
Okay, reaction goes towards the stable base.
Precisely. So if you're looking at a reaction where A is the conjugate base on the right side and B is the base you started with on the left, if A is more stable than B was,
then the reaction favors the right side, making A.
Exactly. Let's take a concrete example from the text. Consider hydrogen sulfide, H2S, reacting with methoxide ion, CH3OR. The products would be the hydrosulfide ion, HSOR, and methanol, CH3OH.
Okay, H2S plus CH3OO goes to HSO plus CH3OH.
Right. To predict the equilibrium, we need to compare the stability of the bases involved. That's the starting base, CH3O, and the conjugate base formed, HSO.
Okay, comparing O versus S.
Apply ARIO, factor 1, atom. Oxygen and sulfur are in the same column.
Same column, so size matters more than electronegativity.
Exactly. Sulfur is larger than oxygen.
So the negative charge on sulfur, HSO, is more spread out, more stable.
Correct. HSO is significantly more stable than CH3OR. Therefore, the equilibrium will lie heavily to the right, favoring the formation of the more stable HSO and methanol.
It makes sense. The reaction proceeds to put the negative charge in the happiest, most stable place it can find.
That's the driving force, always towards stability.
Okay, that clarifies equilibrium. Finally, let's quickly touch on showing a mechanism. Later in organic chemistry, you're always drawing these curved arrows showing how electrons move.
Ah, yes. Mechanisms. The language of organic chemistry.
For acid-base reactions, are the mechanisms complicated?
Actually, no. They are remarkably straightforward, usually one of the simplest mechanisms you'll learn. Typically just one step.
One step, that's nice.
And it almost always involves just two curved arrows. It's like a little electron dance routine that never changes.
Two arrows. Okay, what do they show?
Okay, arrow number one starts from the base, specifically, from the lone pair of electrons on the base that's doing the attacking.
From the electron source.
Yes, and it points to the proton that it's grabbing. So base attacks proton.
Arrow 1, base to proton. Got it.
Arrow number two starts from the bond between that proton and the atom it was originally attached to.
The HA bond.
Right, the electrons in that HA bond. That arrow points onto the atom that the proton is leaving behind, onto A. This shows that bond breaking and the electrons staying with A, forming the A conjugate base.
Arrow 2, HA bond to A. Okay, base grabs H. H leaves its electrons behind on A.
That's it. Two arrows, one step. Now, a key difference from drawing resonance structures is that here, in a mechanism, you are allowed to break single bonds. That HA bond is often a single bond.
Right. Mechanisms break bonds. Resonance just moves electrons within bonds.
Correct. But one rule remains absolute, sacred even. You must never violate the octet rule for second-row elements like carbon, nitrogen, oxygen, fluorine.
No more than 8 valence electrons around them.
Never. They can't handle more than 4 bonds or the equivalent in lone pairs. That's a cardinal rule you always check.
Okay, so practice drawing those two arrows. Base attacks proton, bond breaks onto the conjugate base atom, and it becomes second nature.
It really does. It's such a consistent pattern for all simple proton transfers. It simplifies something that might seem daunting at first glance.
Fantastic. Wow, we've covered so much ground today.
We really have.
From, the fundamental importance of charge stability, why it's taught first, to the 4 key factors, atom, resonance, induction, and orbitals, ARIO, that give you the power to actually predict acidity.
Toolkit.
Yeah, the toolkit. Plus how PK values put numbers on it, that logarithmic scale.
And the equilibrium.
Right, predicting equilibrium based on stability, and even how to draw a basic acid-base reaction mechanism with just those 2 simple, consistent arrows.
It's a lot, but it connects together logically.
It does. And I think the biggest takeaway, for me anyway, is that organic chemistry, which can feel really intimidating at first.
It often does.
It truly reveals its underlying patterns and logic once you grasp these core principles like charge stability.
That's absolutely the key. Keep practicing. Keep drawing those conjugate bases. Keep applying ARIO. Ask yourself, which base is more stable? You will build that intuition.
Yeah.
And it will serve you throughout your entire organic chemistry journey. It's honestly the one secret that makes everything else start to click into place.
So when in doubt, always remember, look for that stable negative charge. That's your guidepost.
Couldn't have said it better myself.
Yeah.
Find the stable charge.
Well, thank you so much for joining us for this depth dive into organic chemistry acidity. We really hope this has given you, our listeners, a clearer path forward in your studies, maybe helped break down some complex problems into more manageable steps.
Hope it was helpful.
Until next time, keep learning, keep questioning, and thanks for being part of our last-minute lecture family.